Unoptimized sequential circuits often contain redundant states. Every extra state requires additional flip-flops in logic gates, increasing the physical footprint and power consumption. To build efficient logic, we have to eliminate these redundancies through a process called state reduction. The most rigorous deductive tool for finding these redundant states is the implication table, sometimes called an implication chart. Its purpose is systematic. It tests every possible state in your circuit against every other state to see if they can be combined. This setup features a state transition table and a lower triangular grid. The stair-step shape compares each pair once. We label the vertical axis S1 to S6 and horizontal S0 to S5. Each cell, like the S1-S0 intersection, tests that specific pair. You will notice the grid omits the diagonal line of cells entirely. That is because a state is trivially equivalent to itself, so there is no mathematical need to test S1 against S1. Setting up this matrix perfectly is the required first step. Without this strict physical framework, tracking the complex web of state relationships manually will inevitably lead to combinatorial errors. With the grid drawn, we begin step 1, identifying undeniable non-equivalence based entirely on output behavior. The rule is strict. We compare the outputs of two states across every possible input combination. If outputs differ for even one input, the two states are mathematically disqualified from being equivalent. Look at the state table. When input x equals 0, state S5 outputs 0, but S6 outputs 1. Because their outputs conflict, we mark this failure by drawing a large X across their corresponding cell in the lower grid. We apply this exact check to every single pair. Any pair with conflicting outputs gets an X, eliminating a large portion of the grid right away. This initial output purge clears the obvious mismatches. It allows us to focus the rest of our analysis entirely on the empty cells, the pairs that still have a legitimate chance of being merged. Now we move to step 2, which deals exclusively with the surviving empty cells. To test these, we use a concept called implied state pairs. Take the empty cell for S0 and S1. We track where they transition. On input 0, they go to S1 and S3. On input 1, they go to S2 and S4. We write these implied pairs inside the cell. If a pair implies a transition to itself, like S1 and S1, it is a trivial pair and can be ignored. We repeat this mapping process for every single empty cell remaining on the board. This chart shows the result. The implication table is now densely populated with next state data, replacing the empty spaces with specific test conditions. Think of these implied pairs as conditional contracts. The present states, S0 and S1, are only equivalent if the future states they rely on are also proven to be strictly equivalent. With our conditions set, we enter the iterative elimination phase. This step requires methodical scanning, as it is where most logical mistakes happen. Look at the cell for S1 and S0. It contains an implied pair of S2 and S4. The dedicated cell for S2 and S4 is already crossed out. Therefore, S1 and S0 cannot be combined and receive an X. To track these failures accurately, we use a strip scanning pattern. We start at the left column and move top to bottom, checking cell by cell, checking the implied conditions against the rest of the board. One pass is not enough. When you cross out a cell, you might invalidate a condition in a column you already checked. You must rescan the grid continuously until you complete a full pass that results in 0 new crossouts. This iterative chain reaction hunts down false equivalencies hiding in the logic. Once the table stabilizes, only the mathematically sound pairs remain. This shows our stabilized grid. We focus on cells surviving without an X. These represent our true equivalence classes. We group them. S1 and S2 become S1 prime. We do the same for S3 and S5, and S4 and S6. Finally, this chart shows the payoff. We construct our new reduced state transition table by taking the original data and replacing all the old state references with our newly merged equivalence classes. We have dropped from 7 individual states down to just 4. The workflow is always the same. Draw the grid, check the outputs, map the implied pairs, scan iteratively until stable, group the remaining equivalents. When you encounter these tables in textbooks, you will often see them ordered alphabetically, displaying a heavy field of permanent X's, leaving only a few clean cells to signify the final equivalencies. Mastering the implication table allows you to take a sprawling, wasteful logic design and distill it into its most precise, cost-effective, and irreducible core.